A generator consists of a coil of wire that is rotating in a magnetic field that is made by some magnets. So a generator generates electricity because as the coil rotates, there is a changing magnetic flux through it. So therefore there is this induced EMF, and a coil will flow in the coil and also to whatever circuit the coil is connected to. So this is how all power generation works, or nearly all power generation works, that you use on a daily basis. So the power that you get from your wall circuit ultimately comes from some coil of wire that is rotating, typically because it's either hooked up to some steam engine or maybe a windmill, or some falling water causes a turbine to rotate and then rotates a coil of wire in a magnet. The only exception to this is really solar power. Solar power does not require generators, but nearly all other kinds of power generation do. So if we want to analyze what's going on inside a generator, we need to look at this coil of wire that's rotating in the magnetic field. So when we look at this, it's easiest to look at the edges of the coil. So let's say we have a rectangular coil, and we can look at what the top edge is doing and what the bottom edge is doing. Both of those edges consist of conductors that are moving in a magnetic field, and therefore there is some induced motional EMF. We won't take a look at the sides because it turns out the contributions from the sides cancel each other out. But if we look at the top and the bottom, we have these two conductors that are moving in the magnetic field. So if we look at that top conductor, so this is a side-on view, we can see that top conductor is moving with some velocity, and the velocity makes an angle with the direction of the magnetic field. So we know that there is going to be a motional EMF because you have a conductor moving in a magnetic field that's equal to the strength of the magnetic field times the length of that conductor times the velocity times the sine of the angle between the magnetic field direction and the velocity vector direction. And there's two of them because there's both the top and the bottom that are moving together. So then we can do some replacing of some of these items if we remember some facts about circular motion. So one of the things we know is that the top and the bottom conductors are both moving in a circle as the coil spins. And we know that the angular displacement is equal to the angular speed times time. That's something we remember from looking at circular motion. So we can replace this angular displacement with omega t. Another thing that we remember when looking at the velocity of this conductor at the top and the conductor at the bottom is that velocity is tangential velocity, in this case, is equal to r times omega, where r is the radius of the circle that conductor is moving in times the angular speed. And in this case, the radius is equal to this side length divided by 2. So we can put that in as well. And if we do that substitution for the velocity, we get this expression. Simplifying it, we can see that the 2's will cancel, and also that the length times the a, so that would be the length here times a, this side, is the area of the coil, or the area enclosed by the coil. So this then becomes a general formula, which is true even if we don't have a rectangular coil. This is an expression that tells us what the voltage is that is generated by a generator, by a coil spinning in this magnetic field. So actually the expression on the previous slide was for a single loop. So if we do have a coil with n turns, then each one of them would contribute the same amount to the overall voltage, and so we also multiply that previous expression times n. And we remember also from circular motion that omega, the angular speed, is also the rotational frequency, and that it's equal to 2 pi times the frequency, where the frequency is the number of complete turns per second. So what this tells us is that the voltage is actually going to follow a sine wave, and in fact it's alternating current voltage. So generators naturally put out AC current. Now in the US this frequency is 60 Hertz. Europe made a different choice, and the frequency that they have in their power grid is 50 Hertz. So we can see from this that a motor is actually a generator run in reverse. So a generator is a coil of wire that turns in a magnetic field and it generates current. In an electric motor, you have also a coil of wire. You run a current through it, the coil's in a magnetic field, and it rotates the coil. So motors and generators are kind of the same thing. One, you turn the coil and you make current. The other, you put current in and it turns the coil. So next, let's look at this example. We have 2 loops of wire, and they're arranged so that a changing current in one, which we'll call the primary, will induce a current in the other, which we call the secondary. The secondary loop has twice as many turns as the primary. As long as the current in the primary is steady at 3 amps, what will the current in the secondary be? So let's draw a picture of what this might look like. So we have a primary loop and we have a secondary loop. Maybe they're arranged like that. Maybe it's different. It doesn't really matter. So let's say first we have a current in the primary loop. So we have some current that's going around, and if we think about the magnetic field that this is generating, we can imagine grabbing this loop to use the second right-hand rule to determine the magnetic field direction, grab the loop, and our fingers, if we do that with thumb in the direction of the current, the fingers would sweep upward inside the loop, outward outside, or downward outside the loop. So the magnetic field would look something like this. So we would have magnetic field being produced by this loop. And some of that magnetic field would be going downward through this secondary loop. So we want to know then what happens if the current in the primary is steady. So if the current in the primary is steady, the magnetic field that it's making is also going to be steady. If the magnetic field is steady, the flux through the secondary loop is steady. It's not going to change. So if the flux isn't changing, then there's not going to be any change to fight against. There's no change in the flux, so there's going to be no induced magnetic field produced by the secondary. There's going to be no current produced by the secondary. So as long as the current in the primary is steady, there's not going to be any current generated in the secondary because there's no change in the flux. So these are the ideas that we looked at. We looked at the magnetic field produced by a wire. Actually, we looked at that during the last lesson, but here's the expression that we came up with. We looked at forces between wires also in the last lesson. And we looked at the magnetic field of a wire loop and a solenoid. So today we looked at Faraday's law, and we saw that current is produced by a changing magnetic flux. Then Lenz's law told us about what direction that current is in, and that it's in the direction that's necessary to make an induced magnetic field that fights the change in the flux. We also looked at motional EMF, how if you push a conductor through a magnetic field, then there will be a voltage generated across that conductor, and if the conductor is hooked up to a larger circuit, there can be a flow of current in that circuit, and then how that principle can be applied to generators, which naturally produce AC voltage or an AC current, and that's how power is generated in most cases.